one last shape that we look at is the rectangular hyperbola. And we've left it to last, even though it's probably the first type of hyperbola that you ever saw, because of course our basic one over there, y equals 1 on x, is in fact what we call a rectangular hyperbola. Any hyperbola whose asymptotes are perpendicular to each other is called a rectangular hyperbola. Okay? So as long as the asymptotes are at 90 degrees, that's a rectangular hyperbola. So what does this mean? Well, we know that if we multiply the slopes together, we'll get -1 because they're perpendicular to each other. All right, let's carry that through. Well, that basically means B equals A for that to happen. Well, if B equals A, the hyperbola now has the equation x squared on A squared minus y squared on A squared is equal to 1. Or a neater way of writing that is just x squared minus y squared is equal to A squared. So, in a funny sort of way, the rectangular hyperbola compared to the regular hyperbola is like the circle compared to the ellipse. Right? The circle was the plus case where the coefficients are the same and it was equal to some radius squared. Well, the rectangular hyperbola is when the coefficients are the same but opposite in sign now. And it's equal to, oh, well, I don't know that we can call it a radius, but it's equal to something squared, A squared there. So the eccentricity, instead of being A squared plus B squared on A squared, it's now A squared plus A squared on A squared. So every rectangular hyperbola has an eccentricity of the square root of 2. So there it is in the position of x squared minus y squared is equal to A squared. So I guess the question is, how do we get xy equals 1 or y equals 1 over x, which we're used to seeing it? Okay. Well, I'm just going to rotate. Okay. When it's in x squared minus y squared equals A squared, those asymptotes have the equation y equals plus or minus x. Remember, the asymptotes were b over a, but b and a are the same now. So it is just y equals x, y equals 1. So I know those asymptotes are at 45 degrees. So to get them being the x and y axes, I just need to rotate 45 degrees. So I've labelled the asymptotes capital Y and capital X. So this asymptote I want to rotate and it'll become the x-axis, and the capital Y I want to rotate, it'll become the y-axis, and then the hyperbola you'll see will be in the traditional spot. Question is, how on earth do I rotate? Well, what I do is, instead of saying, hey, that's a number plane, I'm now going to call it an Argand diagram. And we know rotation in the Argand diagram is multiplication. So if I call my random point that's on my hyperbola xy, but on the Argand diagram it's representing x plus iy, I want to rotate it 45 degrees, so I'll multiply it by cos 45 plus I sine 45. And that should get me the new position. So, all right, x plus iy times cos 45 plus I sine 45. Cos 45, sine 45, they're both the same, 1 over root 2. Expand that whole thing out and collecting real and imaginary. And we see that the real part is x minus y on the square root of 2. The imaginary part is x plus y on the square root of 2. So capital X, because capital X is like my new axis, but that's going to be the real part. So the real part was x minus y on the square root of 2. And capital Y is the imaginary part, x plus y on the square root of 2. We need a neat relationship between the two, but we can, well, it's not so much cheat. We kind of know where we're heading to. If I multiply x and y together, I get x squared minus y squared on 2. But notice that's little x squared minus little y squared. Hang on, I got an equation for that. Little x squared minus little y squared is
A squared.
Thank you. Which is a constant. And so there it is. X times y is equal to a constant. which is what we're used to seeing for a rectangular hyperbola. So there it is in all its glory. So what will be the focus? We know when it was in its traditional position, the focus is AE naught, but we're going to rotate that 45 degrees. Well, A, remember, eccentricity is root 2, so it becomes root 2A. Multiply that by cis 45, and look at that, it's kind of neat. It just becomes A plus AI. And so it's AA. And the other one will be minus A minus A. The directrix. This one's a little bit trickier because now we're talking about a line rather than a point. So originally we had the line x equals plus or minus A on E. And we're going to rotate it 45 degrees. Again, we know the eccentricity is the square root of 2. So I can make that A on the square root of 2. Right. So it's going to start off, the directrices are parallel to the y-axis. I'm going to rotate it. It's still got to be parallel. So if I rotate it 45 degrees, and we were going, hang on, which way did we go? We went anti-clockwise. So now they'll be parallel to y equals negative x. So I know the slope of the directrix in the new position will be negative 1. In other words, the equation will be x plus y plus some constant is equal to 0. Just got to work out what that constant is. Well, I know that the distance between the two directrices, if they have the equation a on root 2 and minus a on root 2, then the distance between them is 2a on root 2. Now when I rotate them, that distance doesn't change. But I'm rotating around the origin. So I could say the perpendicular distance from the origin to my new line will be 1a on the square root of 2. All right, well, let's use the perpendicular distance formula. Subbing in the origin into the equation of my new directrix, x plus y plus k, well, x and y are both 0, over the square root of 2 is equal to a over the square root of 2. Lovely. Look what happens. K is a and minus a. So we get a lovely little equation there too. The directrices are just x plus y equals plus or minus a. So to summarise that, once we've got the rectangular hyperbola in the position that we have been used to seeing before we started on our conics chapter, where x and y are the asymptotes, it will have the equation xy is equal to a half a squared. So that constant will be a half a squared. Once we know that constant, we can work out the foci will be plus or minus a plus or minus a. The directrices will be x plus y is plus or minus a. Eccentricity is always the square root of 2. But when we do a parametrics, instead of making it equal to a half a squared, remember it's just a constant, it's easier to just call it c squared. And that way, all I've got to do for parametrics is say, well, x is ct, y is c divided by t. Because if I multiply those two together, I get c squared. And so my parameter t is the one that links the x and the y value. So the parametric form for the rectangular hyperbola is similar, I guess, more like the parabola that we saw. Remember, it was 2ap, ap squared, so it just had one letter. Whereas what we saw with the ellipse and the hyperbola had an angle that was linking the two together. We could work out the tangents in the normal way that we do, point slope formula. It turns out to be x plus t squared y is 2ct. And the normal is this beautiful expression there. T cubed x minus ty is a constant outside of t to the power 4 minus 1. Quarter contact. As this is similar to our parabola last year, this time I'm going to derive it like we did the parabola last year instead of doing the cheat method that you don't like so much. The equation of any chord, we've got to find that first of all. So we give P and Q some random coordinates. CP, C on P, CQ, Q, C on Q. The equation of PQ will end up being x plus PQY equals CP plus Q. That's just any chord. Okay. We then find the point of intersection of the two tangents. And it'll end up having these beautiful coordinates, 2CP on P plus Q, 2C on P plus Q. But remember, we will know the external point is x0, y0. So x0 must be 2CPQ on P plus Q, y0 is 2C on P plus Q. So, substituting back into our equation of the chord, remember we're trying to eliminate the parameters, so P plus Q and PQ. Well, the first one I've substituted in for there is, where are we? X plus PQY, but I've rearranged, where was it? PQ, there's PQ, with the x0. So PQ was equal to P plus Q times x0 divided by 2C. And on the right-hand side, I've just left it at the moment for CP plus Q. But I could now use my y0 coordinate. I could make P plus Q the subject of this one. And I can get rid of the P plus Qs. And now I have no P's and Q's. There's the equation. Looks horrible. So let's make it look nicer. There it is. And whether you can see it or not, and possibly you can't see it, once again, the chord of contact mimics the equation. The equation, remember, was xy equals c squared when we had it in parametric form. We'll have a look at what I've got. xy naught plus x naught y is 2c squared. Well, imagine the zeros weren't there. I'd have xy plus xy is 2c squared. 2xy equals 2c squared. xy equals c squared. So there's our chord of contact. So again, if we just know that, let's not worry about doing all this working out unless they force us to through their question. We know that, okay, it will look like the actual equation itself, but I'm going to need two of them. This one where I can put the x naught in, one where I can put the y naught in. So on the right hand side we end up with 2c squared instead of 1c squared. Someone asked me yesterday about locus questions. Maybe it was out of fear, I don't know. That, hey, we've been doing all this work, but we haven't done any locus questions like we did with the parabola last year. Well, what the syllabus says in conics is the only shape that we will get locus questions on is the rectangular hyperbola. So that's why we hadn't seen any yet. You could still be asked about geometrical properties and all those things, but when it comes to actually find the locus of a point, it'll be a rectangular hyperbola question. So let's have a look at the palindromic here of 1991. Hyperbola H. Sometimes they like to give these hyperbolas a name. Maybe it makes them feel wanted. I don't know. Is xy equals 4. Sketch H. Now there's a gift question that year. Sketch H, where H intersects, showing where H intersects the axis of symmetry. Okay, number plane, hyperbola. There you go, I've sketched H. There's the axis of symmetry, y equals x. There is another axis of symmetry, of course. And why didn't I draw it? Right, so y equals minus x. It doesn't intersect that one, so I didn't bother drawing that axis of symmetry. So showing where H intersects, where would this intersect? 2, 2. Because x times y is 4. It's on y equals x. So 2, 2. And if you couldn't work it out, you could go back here and substitute in and go, x squared's 4. Plus or minus 2, so there's 2, 2. And minus 2, minus 2. Another sort of traditional question, go and find the equation of a tangent. But they've given us the equation, which is nice, because it probably means we're going to use that equation in a subsequent part. So if we can't get it, at least we've got it to use. Show that the tangent at 2t, 2 on t, is that particular expression. So I need to work out a slope, differentiate dy dx is minus 4 on x squared. We want at the point where x is 2t, we get the slope minus 1 on t squared. Point slope formula. Playing around with it, and there we go. There's our equation. So s cannot equal 0. S squared cannot equal t squared. Show that the tangents of P and Q intersect at 4st on S plus T, 4 on S plus T. Why can't S equal 0? Right, because if we have a look at the coordinates of Q, S would be on the bottom of the fraction there. So that's the only reason they've said S can't equal 0. Why can't S squared equal T squared? Right, well the other point was 2 on T. So E can't equal 0. But also you've got this S plus T on the bottom. So S can't be the negative of T. Well, another way of saying that is S squared can't equal T squared. They can't be the same, because then they would be the same point. So it can't be plus or minus. So that's the only reason that's there. It's just to sort of, I guess, clearly define the question. It's not something we have to worry too much about. We basically want to find our point of intersection. Well, we found the slope of P. We don't have to rederive it. Q, the only difference is we're using the letter S instead of the letter T. So Q must be x plus S squared y is 4S. Let's eliminate the x's. T squared minus S squared. Difference of 2 squares. So I can get the S minus T's cancelling, and there's the y value which we were looking for. Substitute back in. Now, for this type of question, yes, show your substitution step. Because remember, the question is saying, show that the tangents meet at this point. If you were to just go, oh, there's y, therefore x is this. Well, you haven't actually shown x is this. You've just written down what they gave you in the question. So in this sort of question where they give you the coordinates, yep, I'm going to show my substitution step, and that indeed I do get 4st on S plus T. So there's M. Well, whenever we find the coordinates of the point, what usually comes in the next part? Find the locus. Here we go. Oh, what a surprise. Suppose that S is minus 1 on T. Show that the locus of M is a straight line through the origin, but not including the origin. Okay, so we know X is 4st, S plus T, Y is 4 and S plus T. We've been given the additional information, S is equal to minus 1 on T. That actually is very similar to the parabola questions, isn't it? Because if you think about it, what they're saying is the two parameters multiply together to give -1. So it's very much like those focal chord questions we did with the parabola. PQ is equal to -1. But then what that means is, have a look at my x value. S times t is -1. Well, I can get rid of the st, and x and y become very similar. X is minus 4 on S plus T. Y is 4 on S plus T. There's my locus, y equals -x, which would be a straight line which passes through the origin, but not including the origin. Why can't it include the origin? It's even simpler than that. Remember, our locus are all the possible points for M. Why can't the origin be one of those possible points? Divide a positive number, you can't get 0. So yeah, have a look at the y value, 4 on S plus T. Well, that can never equal 0. Right? Constant on the top of the fraction, can't divide a constant and get 0. So y is equal to -x, but look, 4 on S plus T can't equal 0, therefore we can never have the point 0, 0. If you think of the picture, let's just look at that hyperbola over there. We're talking about the point of intersection of two tangents. And we're saying it can never be the origin. And that's because that's where the asymptotes meet. The asymptotes could never be tangents to the hyperbola. That's basically why we can see you could never draw two tangents that would meet at the origin there. Okay. Patel, good old Patel. 16. You hate Patel? Oh. somewhere, I don't know where Patel lives, but somewhere right now, he's crying. And then there's fake Cambridge.